All right, so we're going to start atomic and quantum theory. First, it'll be atomic, and then we'll move to quantum, because we need quantum to explain atomic. So, just looking back at what we've done so far this semester, we looked at magnetism, electromagnetism, and we ended electromagnetism with James Maxwell's equations of figuring out that electromagnetic radiation is really waves, light, what we've called light all along. Maybe ultraviolet, maybe infrared, but the electromagnetic spectrum has the visible light inside of it. Okay? And then we went from that to use light in mirrors and lenses. But now we need to go back to light itself. Because there's an age-old question that bothered scientists, that bothered physicists for hundreds of years. And that question is, what is light? Isaac Newton lived in the 1600s. Isaac Newton said, light is a particle. And you could see it. Light would strike a surface and reflect off, just like a ball would strike a surface and reflect off. Okay, so it looks like light is a particle to Newton. And, Newton was right on an awful lot of things. So people were okay believing him. But then, the stuff in electromagnetism that we just finished, before mirrors and lenses, and so Newton, this was like 1660s or so. Okay, so then James Maxwell, I'm going to say 1880. In 1880, and even before James Maxwell, so mid-1800s, people were looking at the fact that light was probably a wave. It was probably a wave because they could see it interfering with itself, right? You remember when in grade 11, we used the ripple tank, and we did interference between waves, and we know sound waves interfere, and light interferes with itself. Two sources of light will interfere. So they thought, light must be a wave. And we also know that light diffracts, just like sound diffracts. Right? And if you remember, diffraction is, again, in the ripple tank. Remember, we had a barrier, and we sent water waves into a little opening, and the waves went through the opening and then spread out on the other side. Diffraction is the spreading out of a wave beyond a barrier or around a corner. And so just like water waves, just like sound waves, light diffracts. So light must be a wave. And then we also know that you can polarize light. And polarization is when you separate out the different vibrations to just one. It's what your sunglasses do. And only transverse waves can be polarized. So light must be a wave. And then we also know that the wave equation, V equals F lambda, for light can become C equals F lambda, where light has a frequency and a wavelength. If light has a wavelength, it must be a wave. And then the final nail in the coffin was James Maxwell. James Maxwell, who showed that light and other electromagnetic radiation could be described as waves being given off as energy, as a result of electric and magnetic fields interacting. Okay? And he came up with his 4 famous Maxwell equations to show this. So, like by 1880s, light was a wave. There was no question light was a wave. And poor Newton, well, I guess he was wrong. You got to be wrong now and again. But then, by the late 1800s, 2 things came up that could not be explained if light was a wave. One was that when light strikes matter, some of its momentum is transferred to the particles of the matter. When light strikes matter, some of the light's momentum is transferred to the particles of the matter. But if light's a wave, how does it have momentum? Light must be a particle if it has momentum. So it couldn't, the fact that when we shine light on matter and some of the matter's particles picked up momentum as a result, indicated that light must be a particle. The second thing was that when light struck some particular metals, that it causes these metals to emit electrons. It's almost like it was knocking the electrons off or something, and it could not be explained by what we now call the wave theory of light. So this would be the wave theory of light. And Newton and these two experiments tend to indicate that light should be a particle. So it was called the particle theory of light. And so from the 1600s, Newton's time, right up to the 1900s, really, they were arguing light's a wave, light's a particle, no, light's a wave, no, light's a particle. And neither theory could explain all the different things we were seeing with light. And one of the important characteristics of a theory is that it should be able to explain everything that we're seeing, and it should be able to predict what's going to come. And neither of these theories could explain it all. And so the arguments went on, and just when they thought it was settled, it was like, oh, maybe not. Well, finally it gets settled. And it gets settled by someone that you've been waiting in your physics life to make an experiment. It gets appearance. It gets settled by Albert Einstein. Okay? And Albert Einstein settles it, it's the early 1900s, and he settles it in a brilliant way. He settles it by what he calls his theory of the dual nature of light. He recognizes that neither of these two theories can completely describe how we see light acting. And he says, well, maybe light has a dual nature. Maybe sometimes light acts as a particle. And when we look at it, we realize light acts as a particle whenever it's interacting with matter. So when light is interacting with matter, it acts as a particle. And sometimes light acts as a wave. And light acts as a wave when it's interacting with other light. And so it's called the dual nature of light, and it's really not that difficult to understand when we think about, well, we have dual natures too. Sometimes you act as differently in one situation than you would in another. So when you're with all your friends and you're being cool in the cafetorium at lunchtime, you're probably not acting the same way as you would in my physics class. We tend to act the way that the other objects act that we're hanging out with. So when light hangs out with matter, it acts like a particle. And when light hangs out with other light, it acts like the other light as a wave. And so it's known as the dual nature of light. And we're going to now look at the two experiments, these two things that caused us to say, oh wait, maybe everything isn't explained by James Maxwell. Okay? And so the first one we're going to look at is a really famous experiment. It's called the photoelectric effect. And so in the next video, we'll take a look at the